All right. Hello, everyone. Welcome. Today we'll be going over support vector machines, or SVMs. These are a classification model that is very lightweight and hopefully easier to understand than previous meetings that we did on neural networks and different modifications of neural networks. Can I get a quick raise of hands of who here was at a previous meeting, previous AI Club meeting, just to see if there's any newcomers? Okay. Mostly new people, mostly returning, some new people. That's perfectly good. Before I forgot, let me unfreeze the screen. Cool. So, one of the things that we should know before going into support vector machines are linear regression problems. Can I get a raise of hands if you know or understand or have even heard of linear regression as a model or as a problem? Perfect. All right, cool. We're all on the same page, but quick recap. The goal of a regression problem is to find a line that best fits a data set. So in the example that we have up here, we have all these data points, and the goal is to find a line that predicts a data point given some information. So for instance, given the X, predict the Y. And the way we could do that is we start off by just randomly guessing a line that can fit the data. Usually this is a very awful guess. We can make some educated guesses, but for instance, we could just start with a vertical or horizontal line at the y-axis. Yeah, a horizontal line. And we can then identify how well that actually fits the data set. And to do so, we can do what's called finding the residuals. So if you guys can see down here in the bottom graph, we can see kind of our predicted value, or that line of best fit, and each of these data points in red, these data values. A residual is the distance between that line and the data value itself. Just kind of identifies how well does this line predict the data. So the goal would obviously be to minimize all of these residuals. And so if we're able to find a line where the distance from the line and every single point is as small as possible, it means we did a good job. The farther the larger the residuals, the worse the line actually matches with all the different values. To do so, we use a little bit more complicated things. So just summing it up, we use what's called mean squared error, where the error, or the distance or the length of the residuals, is squared and then taken the average of. Does that make sense to everyone, the concept of mean squared error and residuals? We get some thumbs up, thumbs middle, thumbs down. Thumbs up, perfect. This is pretty much the introductory to SVMs. So a quick recap, regression is find the best line that fits the data. However, with SVMs, we aren't doing regression problems. Yes, we can solve regression problems with SVMs, but for the most part, we'll be using it for classification. Who here remembers what classification was? Does anyone want to take a shot giving the definition of a classification problem versus a regression problem? Yeah, go ahead. Exactly. Regression, we're trying to predict a value, things such as an integer or a float, whereas in classification, we're trying to classify or identify a label or class of data. So for instance, here, we have a very simple graph. Let me actually turn off this. Yeah, that looks a bit better. So we have here two classes of data, right? We have our green data points and our red data points here. And so the goal is to find a way that we can predict whether a data point is green or red based off of the location or the different information about those data points. So if we remember from before, what is a good way of splitting up this data? Can someone give me a good way that we can figure out how to split these data points? I want to take a shot at how we can split this. You could be as logically correct or just row one. Yes. Yeah. So we can use clustering algorithms like k-nearest neighbors that we covered in the fall, or I won't be going over that too much today. One other thing we could do is we can take a book from the linear regression and build a line that kind of splits that data apart. So for instance, if we look here, we can use a hyperplane to split the data. This yellow line is a hyperplane. That's line be a plane or whatever you call it, four-dimensional version of a plane. I don't know. But we can use some kind of splitter to separate the data. How do we think that this hyperplane is a good way of splitting our data into red and green data points? Yes or no? Someone want to shout it out? No, it doesn't do a very good job. I mean, if you try to split it above, we have mostly reds, but there's still some greens below. I mean, it's not a very good job. So we can go ahead and adjust this again. Now we've moved our hyperplane, so now it's actually split our problem. And so see here, anything below the hyperplane is a green class, everything above is a red class. However, do we feel like this is the best way of splitting our data set? Yeah, thumbs up, thumbs down. Do you think this is the best way, or do you think that it could be improved a little bit? Yeah, I see a lot of it could be improved a little bit. Does anyone want to take a shot of how we can improve it? What way do you want to change the line? Do you want to rotate it, shift it? Do you want to take a shot at it? Because there's all the right answers. This isn't the best line. Yeah, go ahead. Like that, right? Exactly. This is a better split. But really, what we want to cover is a bit why. We'll get into this in a second. As I mentioned before, hyperplanes could be different dimensions, because in the case of before, we were only looking at two dimensions, right? We have our x and our y dimension. But we've seen examples where we have over 50 dimensions of data, in which case it's kind of hard to visualize a 50-dimensional plot. But even in the case of a three-dimensional plot, we could see that the hyperplane is a plane rather than just a line as shown in a two-dimensional one. So just to keep in mind, when there's more dimensions, this hyperplane also increases in dimensions as well. All right, so going back to figure out which hyperplane is better, we've already discussed that we like the one on the right better. But how come? Can someone give an opinion as to why they think the one on the right is a better split of the data than the one on the left? It could be technical or not technical explanation, up to you. Just why do you think one's better than the other? Yes. So you think, let me see if I'm understanding. So if, for instance, any line that has a slope closer to -1 tends to look better than ones that have like a steeper slope, is what you're saying? Okay. I mean, that's one way of looking at it, saying, hey, if the line looks more familiar to us, that could be improvements. Yes. Yes. Mhm. Yeah. So what you're saying is it's the residuals are more consistent on the right side than on the left side. Yep, that's one good way of looking at it. Another thing that I guess we'll touch on a bit later is not only is this more consistent, but there's like less outliers. So for instance, distance from this line to here is much larger than from here to here. If you look at mean squared error loss, it exemplifies outliers because we actually square those residuals. Again, it's a bit more of in the woods explanation, but that is a very good point they put out. It's more consistent than this one. Do you have your hand raised? Mhm. Yep. So like one over here, we can see it's very, very close to the nearest what near the nearest data points are very close to the hyperplane. Whereas over here, all of the data points are kind of spaced further out. And that is kind of exactly what SVMs do, especially hard margin SVMs, which is kind of going to be the starting point for the basic way of splitting our data. So as we talked about, this is a hyperplane. The goal of a hyperplane is to perfectly separate our data. And so that's the key difference between a hard margin, and we'll go over later a soft margin. Hard margin SVMs only work when we're perfectly splitting the data set So there is no outliers on both sides. Another key concept is this type of maximum margin hyperplanes, which are hyperplanes that are parallel to this main hyperplane here. So for instance, they'd be right here. And so as we talked about before, we want to find a hyperplane that is as far away from all the data points as possible. And so, like I mentioned, the goal is to have a hyperplane and these maximum margin hyperplanes that are parallel to our original hyperplane that kind of go along those neighboring data points, which we'll define in a bit. And when I say maximum margin, that's because we're trying to maximize the distance between these two parallel hyperplanes. That distance between the hyperplanes is considered the margin. The goal is to maximize, to find those parallel hyperplanes that splits the data points furthest from one another. And that is the goal of the hard margin SVM. The reason why we call them SVMs, or support vector machines, is because the data points along those maximum margin hyperplanes are the support vectors. They help support these hyperplanes. I know this is a lot of terminology all at once, but we'll go play around with this in a bit. But how do we feel about the concept of having these maximum margin hyperplanes that try to maximize the distance between them? We're not going to how it does it yet, but just the concept of trying to find a line that maximizes kind of the distance between the points. Yes. Yes, they essentially just go over those support vectors, as we call them. And yeah, we go through the support vector. Sometimes it only goes through a single support vector. Sometimes it goes through multiple, as you see here. They do go through 2 support vectors each. But again, the goal is to find a hyperplane that maximizes that margin as previously mentioned. Does anyone else have any questions about the hard margin SVM? We'll show a couple more examples in a bit. To get some thumbs up, thumbs middle, thumbs down, people's understanding and how they're following this so far. Thumbs up if you feel like you understand. Thumbs middle if it's like a little bit more explanation needed, or thumbs down if it's good. Oh, cool. So most thumbs up. Hopefully this will clear, the next couple of slides will clear up some more things that are interesting. So here, this is the other line that we said was worse, right? Well, if we build those maximum margin hyperplanes with this as our hyperplane, we get kind of these worse off maximum margin hyperplanes. You see this margin here, it's a lot smaller than we have in the previous example, right? If we check this one, the margin is huge when we have that line closer to what you said was a -1 slope. If we change it back to that more vertical slope, those maximum margin hyperplanes are much closer together and the margin is significant. So we can use that as a more concrete or quantifiable way of identifying what a better hyperplane is. Does that clear up some misconceptions about this? Hopefully we're on the all right, cool. And this is the exact or the optimal hyperplane with the maximum versions of those margins. Cool. You want to cover some of the math?
Sure. Okay. So if you guys look over here, we can see that the red line here is the boundary. This is the actual classifier there. So what that means is on that line, the value of our weights times our support vectors minus some sort of bias is 0. So the points here are not distinguishable. We do not know what they are if they sit on this boundary. But for a hard margin SVM, where we are able to cleanly separate the data, this does not matter. We don't have anything there. We know what classes everything belongs to because everything is separated and past the maximum margin, the maximum separating hyperplane. So what we can look at here is the way that it classifies. So these 2 points here, the blue ones that are kind of bolded, those are our blue support vectors. And for those to be considered support vectors, they need to lie on this maximum separating hyperplane. So if the values that we get by multiplying the weights associated with each of those points minus the bias is greater than 1, then it's class A. And if it's less than -1, it's class B. And it's very important to note, for this system to work, there will not be values that lie in this space here. There are no like negative fractional values at like between 0 and -1, and there's no positive fractional values between 0 and 1. For hard margin classification, the closest points have their value set on the maximum separating hyperplane. Does this make sense for everyone? Cool. Okay. And again, very, very important. For this system to work whatsoever, points need to lie outside. And this is kind of why, if you compare this to how linear classifier does something, with linear regression, for example, and we're able to tell which line is better because we're able to know more likely which it is. This system allows us to estimate with a stronger strength what class it should be belonging to. Because we know where the line is, we're able to figure out, oh, this point's really far away. It's going to have a very positive value. It means it's very, very likely to be in class A. And if it's very negative, it's very likely in class B. Compare that to linear regression. There's very little statistical stuff. It's just on the side of the line. Yeah. W and B are unknowns. Yeah, so so here, it explains here. So the size of the margin, as far as I'm aware, it should just be 2 divided by the norm of W, which should just be the weights. And then, yeah, B, as far as I'm aware, is just the intercept. It's more or less just doing linear regression, but then making sure that the line separating it is the space between the two classes is as big as it possible. How are we feeling? Good, medium, not so good? Any questions about this? Because it's like kind of mathy a bit out there. Just tell class A from class B as much as possible. Feeling good? Let's get going.
All right. So, as we mentioned before, hard margin SVMs work only when we're able to perfectly separate the positive and negative data points. However, that's oftentimes not possible or requires very strict lines that can often result in overfitting, which, if you don't know, means kind of like over memorizing the data, not really learning general trends, but being too intricate with our training. So for instance, this data set is not as nice as we saw with the previously separable data points. And so if we try to build, let's say, a linear line, it's just impossible to get a perfect linear boundary for this. So this hyperplane would not be a perfect split of this data, because we see here, most of the green are below the hyperplane. But there's that one green outlier that kind of throws it all off and kind of ruins the hard margin SVM.
And to be clear, a hard margin SVM would not converge here. The SVM is really cool because if your data is cleanly separable, you will always converge. But in this case, the data isn't cleanly separable, so a hard margin SVM will not ever converge. You could run it infinite times, but there's no way to cleanly separate the data, so we'll never actually classify it. So keep going forever. Make sense? Yeah. It's rudimentary, and it is too niche, which is why we're going to cover something that isn't.
Yes. As we just mentioned, if you didn't hear, hard margin SVMs, they're not perfect. They don't work on pretty much all realistic data sets. And because of that, we need to find a new way of finding this boundary. Yes. Yeah. So there's a bunch of ways. We've only been showing linear SVMs, these kind of things that break it linearly. However, sometimes we can also choose to do non-linear hyperplanes. So for instance, we have this example, right? Does this split the data? Yeah, but is this really what we're looking for? Maybe sometimes when we really try to split our data with these non-linear classifiers, we can end up memorizing the training data a little bit too much, which results in worse test accuracy, which we've covered a little bit in previous workshops. But the main idea is that you don't always want to fit the data exactly with nonlinear hyperplanes, and also linear hyperplanes don't necessarily represent the data well, especially if it's not a perfect split. And to accompany this, we have something called soft margin SVMs. Soft margin SVMs kind of remove the concept of those maximum margins with the goal of just finding the maximum or the distance between the line from every single point. So does everyone remember the concept of a residual from the linear regression problem? Yeah. Well, this pretty much takes that and uses it to find our new hyperplane. And so the residual, just as a recap, is the distance from the line that we're predicting to every single one of the points. And the goal is to, one, make sure that the residual is in the correct direction. So that means we're predicting the right thing. So for instance, if we look at this one, so if we look at the below the line, we expect them to be of a green label or green class. That would have a positive direction or a positive residual. So if we look at this one, this would be in the positive direction, positive residual, because we are predicting it correctly. However, if we look at this outlier here, that's on the wrong side of our splitting hyperplane, we could see that it is a negative residual, something that we want to avoid. And because of that, we now have a quantitative way of identifying how well the hyperplane splits our data. We just use the residuals, a similar concept to linear regression, but instead of using that mean squared error loss, we like to use what's called hinge loss, which we'll go into the next. So hinge loss kind of looks like just a very simple linear line. So it just whatever the hinge loss, whatever the residual is, that's the loss, especially if it's negative. But at a certain point, we cut it off and just say, hey, if it's very far positive, it's going to be 0. So for instance, if the data point is on the correct side of our hyperplane and is decently far from it, then we have a loss of 0. That's hey, we've perfectly predicted it with 100%. It's nowhere near our hyperplane that splits the data. That is a good job. 0 loss. And so for instance, that's what we see here. It's predicted on the correct side, and it's far away from our hyperplane, therefore 0 loss. However, just because we predict on the correct side doesn't always mean we don't want to disincentivize the line from being that close. So for instance, if we have another data point that is on the correct side of our hyperplane, but is pretty close, we want to say, hey, maybe we want to push the hyperplane a little bit further away just so that we can be a bit more confident. And therefore, we will still have a positive loss, but it's not something that's like a significant effect. So having a small positive residual will result in a small amount. Not too much, which we'll see it will grow as we get to the negatives. On the other hand, if our residual is negative, meaning we've misclassified that data point, but it's semi-close away, then our loss starts to increase. So if you remember before, with a small positive loss, it's loss about 1. With a small negative loss, or a small negative residual, we have a kind of an increasing loss here. And the further away we get in the negative direction from our hyperplane, the worse and worse our loss gets. Does that make sense? You have a question? So our loss caps off at 0. Once we have 0 loss, it means our splitting hyperplane is perfect. So for instance, if our data point was like way over here, that would still have a loss of 0, assuming it's predicted. However, if it was in the negative side, oops, correction. So yes, this has a loss of 3, but let's say our green data point was way over here, the loss might be 10, because there's no limit as to how large loss can get in the negative direction. However, in the positive direction, once it hits some threshold, this can vary and can be a hyperparameter when you go to play around with the model. You could choose at what point it cuts off and just says, hey, this is good enough. We'll call this a perfect prediction. That's why we have a loss of 0. Couldn't have done any better. And I think that's it for hinge loss. You want to explain that?
Yeah, easy enough. So here's the actual equation. More or less what we're doing is we're taking the maximum value between these two things. If it is less than 0, then yay, we can't have negative loss. That means it's pretty far away from the thing, doing really great. And if this ends up being greater than 0, then this is our loss. More or less, this y function here just specifies when we should be considering this. So in this case, if we have like, I don't know, if we're extremely negative, something like, I don't know, a loss of like, if the y function ends up spitting out -2, so we're really misclassifying it, we're going to spit out that we have a loss of -1 brackets. So anything that is, or sorry, greater than, yeah, anything that's greater than 0, we're going to be saying we have loss. So long as we are classifying it somewhat correctly, like Colin mentioned, we're on the correct side, we still have a loss of 1, then we don't really care, it's close enough. But if it's negative at all, if it gets very negative, then we're going to have issues. Okay, go back. Perfect. So basically, this is a max operation. So we're going to be taking the maximum of 0 and 1 minus the function y of basically the way we calculate the value of each position of the thing. So this, you'll remember this equation from the classification associated with the hard margin hyperplane. The y basically just makes it so that we're going to be, I think, just adjust, that's the hinge loss as far as I'm so we pass the output into the hinge loss, we find the residual, and then we do whatever adjustment that we want in order to figure out, should we actually consider this as how it works? And this will inform us how we update the separating hyperplane. Yeah. Yeah. Each point has its own basis. And depending on like what system and what kernel, which we'll talk about briefly, the way you calculate the weight changes. Yeah. Cool. Feeling good? Nice. So we can use this in a number of places. So for classification tasks, this is used a lot of the time in text and document classification because it's very effective. It can handle very robust features very, very effectively. So think about this in terms of like words in a document. You can have 1,000 different words on a page sometimes if you're going with really, really tiny font. And that means that you're going to have a very high dimensional space. Your data is going to be very, very complex. And something you can do is pass it into a model like this, and it'll do a very good job with that classification just because of the complexity of the data. It's going to be able to find a clean class. And then another thing this is often used for is image classification. So compare that to a convolutional neural network. A lot of the time we're able to classify satellite data or handwriting based off of like just the shape of the data. This is high dimension. And we're able to do classification after transformations. And then also regression, but with a bit of an asterisk, and we'll talk about that in a moment. Okay, perfect. So if you want to do multi-class classification, because if you know most tasks you're going to do don't really require you to guess between A and B or true and false, and you have like, for example, with handwriting classification, you want to know exactly what letter it is. You don't want to know if it is a letter or if it's not a letter, because that's very useful. What you need to do is break it into multiple binary problems, and this is done with basically every classifier that we've talked about in the fall and some into the winter as well. What you're going to do is you're going to split it up into multiple tasks. So you can do 1 versus 1, where you make a classifier comparing every single class to every other class. This gives you something like, I think, n times n minus 1 over 2 total classifiers. Yeah, that sounds right. So you're just going to be comparing every single class to every other class and making division lines that way. And then 1 versus rest, which just means you're comparing one class to everything that isn't that class. And that results in the amount of classes that we have. And for 1 versus 1, was that it? No. For one versus 1, what you do is you do voting as well. So you just check every single classifier. You check. You add every time it says, yeah, it's this class, or no, it's not this class. That's it. So you just do voting for classification. Good. Thanks. Nice. Next bit that we want is nonlinear classification, because everything that we've talked about so far is with lines. As mentioned, it's a pretty big weakness. So let's look into it. The main way that these are special and they work so well is using something called the kernel trick. Where basically what we're able to do is map our data onto higher dimensional space. So let's consider this graph on the left of the white cell here. We can see that the orange data is kind of in a circular area, and you're not going to be able to make a line to cleanly separate that. So what we can do using this kernel trick is we can project our data to a higher dimensional space. We can multiply every point in there by, say, like x squared. And then we're able to basically just space it out. We're going to add more information to the data, and the ones that are close to zero are going to be still close to zero in the new dimension. The ones that are far away are going to be higher up. And so because all of the ones that are in the orange circle are close to zero, we're able to keep them together, and we're able to split them with a clean hyperplane and get very easy classification. And this makes SVMs very powerful, because if you're able to know the shape of your data or what you need to do to make it cleanly separable just using an equation, you can classify basically anything extremely fast. Any questions on the kernel trick? Yep, you can look this up. If you look up kernel trick, you will find a Wikipedia page. It will tell you about the kernel trick for SVMs. Math is more complicated than it seems at the outset, so. But it's cool. It's really dope. And if you want to look at like a pretty simple toy data set, there's, I think, a few tools online that allow you to do this. Okay, great. Last little bit we want to talk about is regression, because we've talked about classification, but you can use SVMs for regression tasks. So what you do is technically called support vector clustering, where you just define the amount of groups that you need, either through what's called the elbow method, where you basically just check every single amount of grouping that you want. So like, for example, from 2 groups to 40 groups, because you don't know exactly how much you're looking at. And then you check all of them and see what the loss is over time. And you basically just pick the point of diminishing returns. So if you get like roughly the same amount of success at 7 groups as compared to 8 groups, and you're probably going to want to do 7 groups because it's going to be a bit more general and a better classifier. So you just do it at the point of diminishing returns. You can look up, it's, I think, also called the K-elbow test, if you guys want to use this for some K-means. Or you can just brute force it, where you just pick a bunch of different values and try them and train the entire model and do it again, which is basically what the elbow method does, just like a bit more clean. Any questions? Yeah. For how to divide up the data. So compare this to K-means. K-means, what you do is you just pick a bunch of centroids and you ask it to classify points that are nearby. So for this, instead of picking the groups in terms of like nearby points that it should be classified with, what you're going to ask it to do is add lines to separate. So you're going to be doing basically multi-class classification, or regression in this case, because classes aren't defined, by just arbitrarily defining how many groups you want and like trying to optimize for the amounts. So more or less just letting the computer figure it out. So again, this is very analogous to something like k-means, k-nearest neighbors, where you just can define the k value for the amount of points that you're looking at or the amount of centroids that you're going to be considering. And that allows you to do classification in a pretty powerful way without knowing the classified, the target data. Cool. How are we feeling? Thumbs up, sideways, down. Nice. Okay.
So if we're taking anything out of this entire meeting, just I hope you guys understand the concepts of hard margin SVMs. So getting those maximum margin hyperplanes that maximize the margin or the distance between those 2 hyperplanes. This only works for perfectly separable data, which not everything is like that. In which case, or almost always, we'd want to use a soft margin SVM, which uses the concept of residuals, or the distance between the hyperplane and each of the data points, along with the direction, so whether or not it's on the correct side of the hyperplane, along with hinge loss, which is that the concept of where we remove, once it gets to a certain distance away in the positive direction, we just say it has a perfect loss. From there, it just linearly increases as it gets further and further in the negative direction. Those are the 2 main concepts I'd like everyone to take away from today's meeting before we get into the code. Any questions before we jump right into the code? Beautiful.
That'll do us for the recording. Bye bye, people on Zoom.